what we're learning is the European options, puts and calls. That's where you have a very explicit expiration date. The American is where you can, within reason, you can exercise it anytime you want. What do you think is going to be the cost of an American put versus a European put? I just turned around. Don't ask me. Go ahead. What do you think? Okay, what do you think? Didn't look down fast enough, did you? What do you think?
The European one will be more expensive.
Why?
It has more strict rules.
Has more strict rules? What do you think?
Maybe it's an obligation, but not an right. No, I don't know.
Okay. What do you think? What happens is that the European option, March 14th, that's when you can exercise it, when the quarter is over. Okay? But what happens is the American option, tomorrow afternoon. Which do you think is more valuable for you?
The one that's in the afternoon.
Yeah, she says the American option for her is more valuable. Are you going to pay more? Yeah, so the American option probably is going to cost more than the European option. So when we get into the Blac-Scholes equation, we'll be talking about how to price these various things. And what you can expect when we get into the American version, which we will, then you're going to find out that when the American version is going to be more expensive. The put, we're going to come up with an exact equation, and we're going to be using arbitrage to get it. Of course, arbitrage everywhere. We're going to be using arbitrage to get it. And we're going to find out that when the American option is going to cost more than the European option. And it'll be things such as low prices, or such as dividends, or such as all kinds of other things that are thrown into the mix. But we'll definitely get that. Any other quick question? Yes?
So why are puts and calls more expensive? Is one of them more expensive?
A little, one more time.
Like, when is it a put more expensive than a call?
All right. She wants to know when is a call more expensive than a put, and when is a put more expensive than a call? What do you think? So let's make it specific. Let's make it specific. Suppose we're talking about a call for $50, and we're talking about a put for $50 for S. And what I want to know from you is, when is one more expensive than the other?
When the price is larger than 50, the call is more expensive.
All right, he says that when the price is more expensive than 50, that what happens is the call is more expensive than the put. Why? You're right, but why?
Because can't get more money from the call.
You're going to be able to exercise to get more money out of it. Because if what we have is if today's price is $52, well, wait a minute. I'm not going to put the idea of putting it on sale for $50, a $52 object, sure doesn't sound very smart, does it? But being able to buy one for $50, hey, that sounds pretty good, okay? So what happens then is that's what's going to make the difference between them. Okay, you see the common sense on that? All righty. Any other quick questions before we get moving? Oh, darn, I forgot to announce today that you're having a test a week from today. Because I forgot to announce it, it won't be a week from today. I'm sorry. Okay, so it'll be a week from Tuesday, next Tuesday. All right. But it's only because I forgot to announce it. All right. Now, let's, in other words, there's a couple of exams. A lot of you have a couple of exams on Thursday, a week from today. And I don't want you to interfere with those exams. And so it will be a week from next Tuesday will be the first examination. All right. And I'll tell you a week from today what you can expect to be on that examination. Okay. Let's review. We had last time f of x. I have a function f of x, and I want to approximate it. So I'm going to approximate it by f of A, the value of f at point A, plus f prime of A over 1 factorial x minus A, plus f, the second derivative at A, over 2 factorial x minus A squared, plus f triple prime of A over 3 factorial x minus A cubed. That's far enough. Plus other terms. So I'm taking an ugly, ugly function. And what I'm going to do with this ugly function is I'm going to replace it with a polynomial. Polynomials are nicer than ugly functions. Okay, everybody with me on that? Okay, folks, then what we want to do is the following, is I want you to compute e to the minus 0.02. Find an estimate up to a cubic polynomial estimate for the value of e to the minus 0.02.
For what order?
Cubic. Okay, the first trick or the first point is to find what is A. What choice of A should I use? So you choose an A where you know how to substitute it in and to compute what is going to be the value of the function. I'm going to choose an A which is close to x. X here is 0.02, minus 0.02. Close to that number is 0, and 0 is a pretty easy number. All right? So I'm going to choose A equals 0 because it is a number, excuse me, which is close to this number right here. And I know what e to the 0th is equal to. So therefore, I find the polynomial e to the x, I now know that f of x is e to the x, so let's compute the terms and then plug them into the equation. F of x is equal to e to the x. F prime of x is equal to e to the x. F double prime of x is equal to e to the x. F triple prime of x is equal to e to the x. Boy, that was easy. Okay. Now what I want to do is find out, I'm not interested in what is f of x, f prime of x, I'm interested in what is f of 0, f prime of 0, f double prime of 0, f triple prime of 0. So I evaluate it, and I get f of 0 is equal to e to the 0th, which is 1. F prime of 0 is 1. F double prime of 0 is 1. F triple prime of 0 is 1. Okay? And so now what I have is that e to the x is approximately equal, for x near 0, it is approximately equal to 1 plus 1 divided by 1 of x minus 0 plus 1 over 2 factorial times x minus 0 squared plus 1 divided by 3 factorial times x minus 0 cubed. And what we have then is here is an approximation for any value of x. This is approximation for any value of x that's near 0. Minus 0.02 is very close to 0. So I don't know the exact value of e to the minus 0.02, but I have a darn good approximation. E to the minus 0.02 is approximately equal to 1 minus 0.02 plus 1 over 2 factorial times 0.0004 minus 1 over 3 factorial times 0.000008. Okay, everybody with me on that? And so what happens then is that if you have to figure out what is this value right here, a very good approximation is, well, even the first term. This right here is very small. That's going to be 0.0002, and that's going to be a 6, so that's going to be 0.0000001, 3333333, all the way on. It's going to be very small. So a good rule of thumb, okay? Good rule of thumb is that for small x, e to the x is approximately equal to 1 plus x. For small values of x, e to the x is approximately equal to 1 plus x. And where does that come from? That comes from right here. For small values of x, it's 1 plus x. This is going to be incredibly small for small values of x, so let's forget it. This is going to be so small that these look large, and so we can forget this right here. So for small values of x, 1 plus x is going to be a reasonable first estimate. Any questions? Yeah.
I do, but it's not about this.
Oh, we'll wait about this then. What I have then is an important question is who gives a darn? WAGAT. Who gives a darn? So I'll tell you who gives a darn. You have to quickly estimate for me. You have to quickly estimate for me the following. Find the present value of $100. Interest rate is equal to 0.02, and t minus t is equal to 1. I want you to get a good estimate, a reasonable estimate, not a sharp one, but okay estimate of $100 a year from now, where the interest rate is 0.02. 2%. What do you get?
So we have t copy to the 002, so we have 008 times 100.
Okay? And so he's saying that it is $98, and he's correct. Because what happens is the present value of $100 is going to be 100 times e to the minus r t minus t. And what happens is, I said the interest rate is 2%. So this is going to be 100 e to the minus 0.02 times 1, which is equal to 100 e to the minus 0.02. And so what happens then is we know that this is approximately equal to 100 times 1 minus 0.02. 1 plus x. And that is 98. This is 0.98, so this is equal to $98. So $100 a year from now, present value is approximately 98. It's slightly larger because if you throw in the cubic terms, that's going to be plus. Yeah.
So if you asked us that on the test, we'd first have to derive that formula, right?
One or the other. If I tell you to derive it, you have to.
Oh,
If I tell you just compute it by using the estimates, you can write down the 1 plus x and go ahead.
but what about deriving the present value formula?
Depends on what I ask you.
Okay. So
Okay?
if you just tell us to compute it, we can
Yeah.
just use the formula.
So let's use this right now. Any questions on this right here? Let's try it right at the following. What is the present value of $100 a half a year from now? How about you? You. A half a year from now. 99, right? Because if you have a half a year from now, the only difference is I'm going to have 0.02. This, instead of a 1, I'm going to have a half. So this is going to be minus 0.01. So it's going to be 100 times 1 minus 0.01, which is $99. So from this estimate, you can get answers pretty fast. And you need to when we're talking about finance, because we're talking about e to the, whenever we're talking about present value. Okay? So let's tie this in with what we've been doing. Let's do the following. That today, I find out that a stock is worth $102. All righty. And I have that the put at $100. Let's see if I get this right now. And the call at $100. That the difference between these two right here is $6, where their expiration date is 1 year from now. So what I have is the information you have is that you looked up in the market. You had your assistant look up in the market, and your assistant, he told you that the difference between the price of a call and the price of a put is $6 for expiration date 1 year from now. And the current stock right now is $102. What does that tell you?
What interest rate? What is the interest rate?
Oh, interest rate is 0.02. Thank you. Very good. Interest rate is 2%. Thank you. What does that tell you? Arbitrage, the big A, arbitrage. And what happens is, that's because the difference between S and 100 e to the minus 0.02, that's $3. We just computed that. $4. $4. And what happens is, this is $6, and so there's a chance to have an arbitrage of 2. Why is there a chance for arbitrage? The reason is that P at 100 of S plus S has to equal a call at 100 of S plus 100 e to the minus r t minus t. The put-call parity. So if we're going to do this, I'm going to subtract on both sides. I'm going to have S minus 100 e to the minus r t minus t should equal the call minus P of 100 S. And they don't equal. So what are you going to do? So go short of what? Yep. So he's going to say that what happens is this right here, this side right here, costs more, so go short on it. Buy a put, go short on a call. He's going to get, altogether, he's going to make $6 on that. And then with the $6, what he's going to do then is buy, he wants to buy one of these things right here. How is he going to buy one of these things right here? Is he has to borrow money from the bank, that's that minus 100, and buy a stock. So he has to borrow money from the bank, and he has to buy a stock. Yep.
The interest rate will be different if you borrow money from the bank.
Yeah, I know. He's raising a very important question. He says, well, the interest rate, if you borrow or if you sell, are going to be slightly different. Answer is correct. That's because they want to make a little money, just like the horse races. And so what we're doing here is the usual, is not that much different. And to make the equations absolutely correct, are absolutely easier to handle, we say the same interest rate.
So if we make this kind of problem
in the real world, yeah. So in the real world, you will not have absolute equality here. You'll have close to equality, but not absolute equality. The reason is that the interest rate for putting money in the bank and borrowing are different rates. So that's going to make a difference. And in the real world, you have transaction costs. But this is giving you the interest. So what you have to do is check. And also, somebody asked in the extra session we had last night, which I thought went quite well, asked about, don't you really buy in large lots? You can buy in smaller lots, but the larger the lots, the more you buy. Instead of buying one call and one put, you're buying 1,000 or maybe 10,000. The rates go down. Your interest rates go down, the transaction costs go down per unit, etc. So therefore, a lot of these things are bought in large lots. Why? Cost goes down. And so you have that. Okay, any questions on this? Yeah.
So it's supposed to, the right-hand side is supposed to say present value of money in whenever your call or put expires, so your 100-bit rate, but your rate changes. If you buy a call for 2 years, and you look at the present value of money now versus 2 years, that rate can change.
It does.
So how can we pick one rate?
Okay, what happens is we're assuming the interest rate remains fixed. That's okay, that's not what you're saying. But you're saying the present value of money changes. And it does. Doesn't matter with this equation. I look at it with respect to today. Because if I buy this right here is worth about $4. This is worth $6. I sell this, I'm going to earn $6. I take $2 and put it in my pocket, I get this right here for $4. And how do I get this for $4? I only got $6 from here. I got $4 left over. That's the difference between the money I borrow in the bank to buy the stock. So I borrow money from the bank, $98. Put the $4 in there. I buy this for $102. Now, the present value is going to change, but that doesn't matter. I've got the stock and I've got the money from the bank. I have to pay it off. And so on expiration date, everything is equal and I'll be able to take care of everything. Okay? The price of the call and the put are going to change.
Right, that's what, so
Yeah.
when I price it, and if
But
I
it-
look at a year in the future,
Does-
money's gonna change by then.
Doesn't matter. Whatever it is at expiration date, they're all going to equal. That's the put-call parity, remember? The put-call parity at expiration date, no matter what the price of the call, what the price of the put. On expiration date, you know that this equation right here is going to be satisfied. Because it's going to be satisfied, this right here on expiration date is going to equal this right here on expiration date. Here's what you have, here's what you have to worry about. I have a stock, and so if somebody calls, I can give them the stock, etc. No matter what happens, I can handle the situation. That's what he's doing there is he's raising an excellent question. He said, hard part about going on the market is the uncertainty, just like in the horse racing, the uncertainty. Okay? And so what we're doing is that the put-call parity equation helps remove some uncertainty. That the price of the calls and the puts might change, but I know where they're going to end up. And by knowing where they're going to end up, no matter what happens in between, by knowing where they're going to end up, I'm okay. And that is exactly where you get rid of some of the uncertainty. Look at the following. Uncertainty. We're starting off, and you're heading down to Staples Center in LA. And you're not exactly sure. You got a couple detours. I mean, a 405 is always full of detours, isn't it? I think they should call it the detour freeway. All right, so you're driving along there, and you got to go over here, and you got to go over there. You're going all sorts of zigs and zags, but you know where you're going to end up. And by hopefully, and so by knowing where you're going to end up, you can make certain predictions and things like this. And so that's the advantage of it. All right, so it removes the put-call parity equation, helps remove some of the uncertainty in the equations. All righty. Yeah.
Can you talk about what happens to the difference between a call and a put as interest rate changes and as
Yeah, well, we're going to talk about that later in the course. After we get to the Blac-Scholes equation, we're going to see how the values of when the interest rate changes, how that all works. We can already do it now a little bit, can't we? Let's do it right now. Let's take a look at this problem right here. Let's say what I have is the put at 100 minus the call at 100 is equal to the present value of $100 minus the stock. Okay? That's the equation. All right. So let's take a look at the difference between this right here. Suppose R goes from 2% to 10%. What's going to happen to the present value of this dollar right here for a year from now? It's going to go down, isn't it? Because 1 minus 0.02 and 1 minus 0.1, this one says that the present value of $100 is about 98. Here it says it's about 90. So this is going to go down. It's going to be smaller. Correct? So this right here is going to become smaller. When the R gets larger, this is going to become smaller. Assuming the price stays to fix, this is going to become smaller. If that's going to become smaller, that's going to become smaller. The difference. Or actually, larger because, I mean, smaller means that the difference is going to be bigger. And so you just go through this and try it. So what we have here is if it's 0.02, if it's 0.02, this is going to be 98 minus 102. All right, and so therefore this difference right here should be minus 4. And then at 0.1, this is going to be 90 minus 102, so this difference should be 112. Minus 112. Because 90 minus, 112, yeah. And so this difference right here. So by just playing with the put-call parity equation, looking at R, looking at T, T minus T, looking at all of these type things, you should know how to analyze these things. Expect quiz problems, test problems of that type. Okay? If the interest rate goes down, if the interest rate goes up, what's going to happen if expiration date changes, if the strike price changes, etc. Because we have our first equation where we can start analyzing those things. Yes?
Sorry, I have a stupid question. Why would you put your money in the bank if it always goes down with the interest rate?
Well, what happens is we're going to find out when we get to the, she's asking a question, why should you put your money in the bank? It isn't going down. What it is the present value is how much I have to put in the bank today to get $100.
Okay, so you get the money.
Yeah.
Okay.
So what I'm doing is if it's 2%, I have to put in $98 today to get $100 a year from now. If it's 10%, I have to put in $90 today to get $100 a year from now. So I'm getting money. But,
That's confusing. It's like
okay, yeah. It's because it's the opposite right here because we're looking at the present value, yes. Now, a second thing is when should you put your money in the interest rates? When should you put your money elsewhere? And what happens is that that is going to be one of the issues that the Blac-Scholes equation will tell us. Because the Blac-Scholes equation, what we're going to be doing is we're going to be hedging in the way which we hedge. We're going to take a call and a stock, or a put and money, etc., whatever, or stock or something. And then we're going to say, but hey, maybe I want to move out of the market. So we're going to double hedge. And that's how we're going to derive the Blac-Scholes equation, and that's where we're going to go from there. Okay, so I wanted to give this right here to tie in what we've done in the last couple of lectures, and we're going to go on to new material now. So let me quickly remind you. Taylor series. Taylor series are very valuable for finding estimates, rough estimates that suffice for your purposes by replacing a function with a polynomial, which is easy to compute. How do you choose your value A? You choose your value A to be a convenient value near what you want to compute. In our case, 0.02 or minus 0.02 or minus, one of these type values. 0 is nearby, and 0 is a darn convenient value. So we use 0. If you have the natural log, a convenient value there is 1. So what you do is you look for convenient values and you get nice polynomial estimates for functions that you wouldn't have before. I mean, look, e to the something and 1 plus x, you can make the estimate faster than a speeding calculator. Okay? An estimate that's reasonably good. Second point which we have, who gives a darn? You do. Okay? Because particularly with respect to e to the x, you have that in the present value of money. And we know that the present value of money plays a very important role. The present value of money is a crucial part of the put-call parity equation. And by having this, what we need is we need to have a quick estimate of what this is with respect to everything so we can make a decision as to what I should do. Third, in answer to his question right here, how can I use this put-call parity equation? All sorts of ways. One way is to write it in this fashion here where I have E, E, E. You can see then as I change the value of E, how this is going to change. As I change the expiration date, how this is going to change. As I change the interest rate, how this is going to change. How I change the current stock, this is going to change. Know how to handle all of those problems before a week from Tuesday. Okay? What I'm going to do now, which is one of the assigned exercises in the notes that I'll be sending out this weekend, and that is, I've got a function like f of x, y. Many of you have had Taylor series. You may not have had the Taylor series I'm going to describe for you now. And that is, I need to estimate, I need to find e to the minus 0.01 natural log of 1.03. Now that one's not too hard. You can use the Taylor series to do that. So I might have the following problem. F of x, y is equal to the natural log of e to the x plus y. Ugh. Now you're stuck. Okay, now you're stuck. What we want to do is I want to find out how to get a polynomial approximation for a function of two variables. And the idea is exactly as we did last time. What I do is f of x, y, I'm going to find it near a point A and B. So this is going to be equal to C0, 0, the constant term, plus C1, 0, x minus a, plus C1, 1, x, y minus b. That's the only way I can write down a linear equation in terms of x and y. And then I'm going to write C2, 0, x minus a squared plus C2, 1, x minus a, y minus b, plus C2, 2, y minus b squared. And you see what the notation is. 0 means I have the 0th power for y. Here I have the first power for y. Here I have the 0th power for y. Here I have the first power for y. Here I have the second power for y. And you can see what's going to be the next one for the third order terms. C3, 0. I'm going to have, everything's going to raise to the cubic term. So I'm going to have x minus a cubed, y minus b to the 0th power, plus C3, 1, x minus a squared, y minus b to the first power, plus C3, 2, x minus a y minus b squared plus c3 y minus b cubed plus, ouch, more terms. Okay. Okay. Everybody see what I'm doing here? I'm just writing down a general form of a polynomial, nice polynomial, up to the third order. Fourth order, I would do the same thing. I would just continue. Okay? So all I have to do now is figure out what are the coefficients. If I find out the coefficients, I'm in good shape. I'll be calling on you. Yeah, you know it's going to come up. Okay. Now, what I want to do at first is I want to find out what is the value of the constant term. See, this is a constant term, first order terms, second order terms, third order terms, fourth order terms, fifth order terms, sixth order terms. I usually can get away with second order in a lot of problems. How do you think I'm going to find C00, the constant? Got it. What she says is she says, let's get rid of all of these terms. One way to get rid of all of these terms is set x equal a and y equals b. If I do that, I'm going to have f of ab is equal to C00, that's the constant term. This term is going to be a minus a, b minus b, a minus a squared, a minus a times b minus b, etc. They're all going to drop out. So I know what the constant term is, f of ab. Okay? Now, how do I find C10? All right, he says, take the partial derivative with respect to x. He says, we got to get rid of, we got to make this standing off by itself. We want this to be standing off by itself with no term. So he says, take the partial with respect to x. So if I take the partial of f with respect to x, the constant term drops out. This term right here is equal to C10. Then the next term is going to be 0 because there's no x's in here, so that's going to be 0. Then this term right here is going to be 2C20 times x minus a plus, I'm going to have C21 times y minus b plus 0 plus da 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 da. Okay, everybody with me? The idea is just to isolate that coefficient, just to isolate the coefficient that I want to satisfy. Get it by itself. Get rid of all the x's that are on there, okay? But I still have some x minus a's and y minus b's. How do I get rid of them? Yep. So what we have then is the same thing. Exactly the same thing. I have the partial of f with respect to x evaluated at a and b. That's going to be this constant plus a minus a is 0. B minus b is 0. All the other terms are going to have a bunch of zeros in there. They all drop out. The fog has lifted. And we found the coefficient, okay? Yeah, our this morning fog is probably in the high 50s. So you understand what the people in Minneapolis and Chicago and all of them, how they're suffering this weekend, yeah, okay. In fact, I got an email message from a friend in Minneapolis. It was only a minus Fahrenheit, not wind chill, Fahrenheit, regular temperature, minus 20, I think it was. And so, aren't you glad you're out here? All righty. So let's see. If I'm going to have you, I'm going to tell you what it's going to be. The formula for these things, I am going, and part of the homework is to derive that these are the coefficients. For example, how are you going to get C11? Well, I pick on you a lot. C11, how am I going to get C11? I take the partial with respect to y of the function. If I take the partial with respect to y of the function, everything is going to drop out except the C11 term. All the others are going to have an x minus a and a y minus b. Get rid of them by plugging it in. All righty. And so your homework is to derive the following equation. And that is Cij. Cij. That is going to be the term or the ith order terms, and where the y is raised to the jth power. It's going to equal the partial, the ith derivative of f evaluated at a and b with respect to y. To get rid of the y terms, I have to differentiate the y terms how many times? Got to differentiate them j terms, that's right. And then the x are the rest of them, I minus j. Now I'm going to have some other terms. I have to divide all of this number, by j factorial, because if I differentiate one of these things j times, j minus 1, j minus 2, j factorial, and I minus j factorial. Okay, and so your homework will be to derive that equation. You derive it exactly the way we did it in class. You just differentiate it the right number of times so each coefficient is by itself. Take a look at all of the factorials that came down there, all the exponents that came down from the polynomials. Plug in a and b to get rid of all the other terms, exactly the same, and collect terms, exactly the same. Let's illustrate this by finding to the second order, by finding the value of f of x, y equals e to the x natural log of y, and I want to compute e to the minus 0.01 natural log of 1.3. I want an approximation to the second order. To quadratic terms, in other words. So we can get started. I need to know what is f of x, y. What should be the value of a and b? 0 and 1. 0 and 1. 1 is very close to 1.3, 0 is very close to minus point, etc. So then I have to know the partial of f with respect to x. That's going to be e to the x natural log of y. I need to know the second partial of f with respect to x. That's going to be e to the x natural log of y. I need to know the partial. I need to know the partial of f with respect to x and y, and that is going to be equal to 1 over y e to the x. And I need to know the partial of f with respect to y, and that's going to be 1 over y e to the x. And I need to know the second partial of f with respect to y, and that's going to be minus 1 over y squared e to the x. And now what we do is I want to evaluate it at a equals 0 and b equals 1. This right here is going to be e to the 0th natural log of 1, which is equal to what? 0. This is 1 times 0. What's this one equal to? The partial of f with respect to x at 0, 1. What is this equal to? 0 again. And this one right here is equal to 0. Boy, got a lot of zeros. That's going to make everything easier. Next, I want to evaluate these right here. The second partial of f with respect to x and with respect to y. What is that equal to? At 0, 1, that's just equal to 1, correct? The partial of f with respect to y at 0, 1 is also equal to 1. And this one right here? Minus 1. Second partial of f with respect to y at 0, 1 is equal to minus 1. And so what we do is I got a lot of zeros. So this is approximately equal to 0 for the constant term. Plus 0 times x minus 0 for the C1, 0 term. That's because that partial is equal to 0. Plus 0 for the, let's see, what is the, now I'm getting into the first order terms, plus 1 plus 1 times y minus 1 Now I'm getting into this quadratic terms. So the second derivative term is 0 times x minus 0 squared. Yep.
Is it a ln of 1.03 or 1.3?
It doesn't matter. I haven't. Oh, I see. let's do y, and let's do x right here. And then I have to plug in the x and the y's in here next. Okay, correct, thank you. I didn't see the, correct. So I'm finding first in the approximation for e to the x natural log of y, and then I'm going to substitute in the x and the y value. So I have this here so far. I get to the mixed term. That's going to be equal to the partial of f, the partial of y, is right here, it's going to be 1. X minus 0, y minus 1. Plus, the next term is going to be also a minus 1 now. But it's going to be a minus 1 divided by 2 factorial of y minus 1 squared. So there's your polynomial approximation. That's your polynomial approximation for that ugly function. All right, and now to find the e to the minus 0.1, what all you do is everywhere you see e to find that value over there, everywhere I see an x, I'm going to put in minus 0.01. Everywhere I see a y, I'm going to put a 1.3, so that's going to be a 0.3 here, all the way through here. And you get your answer very quickly. This equation is going to become a major tool because we're going to use this to try to derive the Blac-Scholes equation. And we'll use this in something called Ito's lemma. So this is something that you will use a lot. So be sure you know how to find at least a second and third order polynomial approximation for a function of two variables that you can just write it down like that. Okay, any questions? Yeah.
How did you find the value? Is the value for C21 just the one on the right?
The value for this, so the value for C20 is going to be the second partial of f of 0, 0 with respect to x, 0, 1, divided by 2 factorial. And the reason it's going to be 2 factorial, it's that when I differentiate the polynomial, the x squared term, the first time I take the differential, I'm going to get a 2 down here. And then I'm going to get a 1 down here, and I'm going to have a 2 factorial. That's part of your homework, is to show that where that 2 comes from, and why you're going to have 3's, and why you're going to have 3 factorial, 2 factorial, and all these other terms. That's definitely part of your homework. And that's what I want you to be able to handle. I'm purposely not doing it, leaving it for you, so that you say, oh, because after you struggle through it, you're going to say, ah. When we use it all the time, and what happens, you'll find it straightforward. Okay? Any questions? Yeah.
Can we use notations like gradient?
Yeah. Oh, no, we don't know. I don't know what a gradient is yet. I haven't read that far ahead
You
yet.
can't use that in the exams to like.
Yeah, no. And what happens is when you get to second order, it's not gradients don't work anymore.
The Hessian matrix.
Then you got to use the Hessian, correct?
So can we use it in the exam?
Sure. Can they? You know what the, yeah, you know what the Hessians and the gradients are. Yeah, you can. He said yes. Okay. He's going to be doing the grading, so therefore, or part of the grading, so. Yeah, you had, both of you had the, Hessian and the second order terms. They had it in a more complicated version. All righty, any questions? I got one. I'm buying Apple stock tomorrow. And I want to know, what should I worry about? If I'm going to buy, what's going to affect the price of stock as the stock goes up and down? So I'm going to go around here, do a little thinking for a few seconds here. I'm going to go around and I'm going to ask you what you think going on in the real world is going to affect the price of the stock.
Financial reports.
Pardon?
Financial.
Financial reports. Wall Street Journal. New York Times for the Wall Street, these things. What else?
Time of the year.
Time of the year. Okay, the time of the year, the season. How about you? Yeah. What should affect the price of something? Just invent anything. It'll be correct.
New management.
New management style. Management. We know that we have new management at stock. The management. Let's see. How about you? What do you think? What's going to affect this price of a stock or anything? Policy type things. Foreign policy, company policy. So he says policy type issues. So in other words, we're in the midst of negotiations with Iran. We're in the midst of negotiations with Syria. All of those things should affect what's going on. Anything else? Yeah. New product. And so in other words, inventions or current price.
How much people are buying and selling?
Okay. Market information. Yeah.
Dividend announcements?
Dividend announcements. One last one. Anybody? Yeah.
Competitor action.
Competitor, what?
Competitor's action.
All right. Your job is to come up with a model to try to understand how prices will change. Okay, that means what you need to do is you need to come up with an equation. An equation which says that the change in the price is a function of take a look on that other panel. That's what has to be a function of all that information and more. What are you going to do? We don't have football here, but one strategy I remember from one school that I went to, which didn't have a very good team, was on the third down, drop back 10 and punt. Okay? I don't know what to do. So what do you think you're going to do? And actually, that was at Northwestern. And actually, Northwestern almost beat Notre Dame by doing that. They were Notre Dame was out of kilter. So what are we going to do? Here's where I'm going to start warning skepticism. Because you have a problem whenever you're modeling. You want to be faithful to what's going on, but you want to get an answer within your lifetime. Okay? And so what you have to do is you have to make assumptions. Assumptions are always dangerous. Because when I make assumptions, if the market is not doing that, then what happens is you got to worry. You got to worry that, whoa, are my equations worth anything or not? And in fact, that's exactly where we start ending up with market failures, etc. It's when people put faith in equations without saying, oops, the assumptions behind this equation no longer is true. And I'll give you some examples as we go along. So, what do? We can put in past history, etc. We have something which is called the efficient market hypothesis. The efficient market hypothesis. You go to a course in a management school in most, not all, but in most schools in the country, and that's the Holy Grail. That is exactly what goes on. That is exactly what you have to assume. I'm saying nonsense. I'm saying it is a simplified assumption so that I can get an equation. And let's see what it does. I might be able to determine competition, but that's a little hard right now. I might be able to use market information, but that's a little hard right now. Later on, if you're smart enough, you might be able to figure out how to get in. That's a little hard right now, so we're going to find a way to get rid of that. Okay, dividends we're going to handle later. Okay, current price, yeah, I guess I need that. Inventions, boy, I don't know how to put that in there. That's a lot of uncertainty. Policy, where am I going to get that kind of information? Past history, US, where am I going to get that? Financial reports, how am I going to get that? How am I going to put that into the equation? See what I'm throwing away? Everything that's important. Okay. And variables affecting the stock price. So I'm going to state explicitly, I don't quite have time to write it now and give you examples, but I'll state explicitly next time what is the efficient market hypothesis. But I'm going to tell you what it is now and what we get to. The efficient market hypothesis says that the change of the price, it says we make enough reductions. We throw away enough of the stuff that's too complicated to understand at the moment. And when it's too complicated to understand, that gives an opportunity for you, doesn't it? Just as we talked about the arbitrage. So whenever you have a course with the efficient market hypothesis, don't believe it. View it as an opportunity to see where you can throw something else in. It says that the change in the price is going to depend on the price, the time, time to expiration, time to whatever. And random effects. And random effects. So we're taking all the things that we know are important, and we're just saying, well, that's random fluctuation. Everything. There's a lot of uncertainty, so you throw it in here. Are there opportunities to do better? Boy, you better believe it. And the more math you have, the more you look at these things and figure out how to model it, the better your opportunities. All right. So now, what do we have when I have this right here? The efficient market hypothesis, which is going to essentially say, well, part of it says that anything that has already happened in the past is already reflected in the stock price. Anything that's happened, it happens so fast that's already embedded into the stock price. And any information like that is going to be in the stock price right away. Okay? Don't believe that. Okay? We'll talk about that more next time. But what it is it's a way, it is just a convenient way of throwing out what happened in the past is already embedded in the price. What happens on policy is already embedded in the price. What happens in management is already embedded in the price. All of these types of, that's what it does. I don't believe it. There are many, many times when it is accurate. A lot of times when it's accurate, a lot of times when it's not. Alrighty, so that's the efficient market hypothesis that we're going to talk about. What we're going to do in between now is we're saying, well, how do I approximate this? Well, a way of approximating this is that it is some constant times the price times the change in price, change in time. All right? That's what we do for money. The change in money is some constant, interest rate times money times the change in time. So I'm just taking an extension, a Taylor series expansion. And plus some other constant times the change in random effects. This is what's going to be lead us to the Blac-Scholes equation. But notice all the assumptions we're making to get there. We're making assumptions that all the things that everyone in this room knows is important. Competition, market information, current price, on and on and on. We're saying that, when I write down the theory, at least the first theory, I don't need it. And the way we justify it is with the efficient market hypothesis, which says that all of that information we need is already reflected in the price, or everything that goes on is reflected in the price already. But indeed, there's random fluctuations. And essentially using the idea of Taylor series, we just write down the first order terms. We'll be using second order terms a little later. We write down that this is approximated by some constant times S delta T, another constant times the change in the random effects. So where are we going to go from here? We're going to, number one, we're going to talk about the efficient market hypothesis. Number two, we're going to then talk in terms of how do we model random effects. Let's talk in terms of random effects, one thing, we'll see what it is. People are bidding on this. Well, this is a nice marker. You're bidding on it. Okay? Or people are buying markers and I want to know what the price is. Well, she's willing to pay a certain amount. He's a certain amount. He's a certain amount. She's a certain amount. Oh my. We got a random type bidding going on here. So I'm going to have a random variable for her, random for him, for her. We're going to add them together. Maybe take the average or something. but we're going to have to know how to handle random variables to handle the random effects. So that's going to get us to the central limit theorem. And from that, we're going to then know how to write down an approximation for the change in random effects, which again makes huge assumptions that I don't believe. But we get to the Blac-Scholes equations. Okay? And so whenever all of these assumptions are violated, you know something wrong is going on. Number two, yet you can't trust the equations. Number two is it gives you an opportunity as a mathematician or as an economist to look at that and say, but by what I've learned in this course about the second order approximations, etc. You have a question? You have a question? You in the blue? All right, so what I have is that if we're taking a look at the second order theory, etc., maybe I know how to put other things in. And so that's really what we're trying to do, is to give you the tools to be able to take it to the next level. Okay, you know what one of your homework problems happens to be, and that is to justify that equation that I raised. I will give you the rest on your email. I will see you at the game tonight against Northridge. And have a good weekend.
The test,